fundamental theorem of algebra. There are several fundamental theorems of mathematics that are extremely important and powerful. They are all simple statements that all carry heavy weight with them. The fundamental theorem of arithmetic is a very simple one. The fundamental theorem of arithmetic says any number has a unique prime factorization. Very simple statement. If you have a number, it has a unique prime factorization. There's only one way you can break that number down into its factors of primes. That is an extremely powerful tool because that is what public key cryptography, i.e. 90% of internet security, is based upon. Public key cryptography is based upon the fundamental theorem of arithmetic of prime factorization, of unique prime factorization. It's huge. It's absolutely huge. The implications of that one simple line of each number has a unique prime factorization is huge. The fundamental theorem of calculus, when you get to that next year, will be huge. It will be how you will do a very, very large amount of your work in the second semester. It is one of the biggest things in calculus is the fundamental theorem. First semester is almost all derivatives, and then you start doing integrals. When you start getting integrals, you'll get the fundamental theorem of calculus, and you will use it to solve it. It is a big deal. It's really huge. The fundamental theorem of algebra is the same way. It is an absolutely simple statement that's being made, but the implications are huge. So, it's hard to understand the way it's written in the original form. Every complex polynomial of degree n greater than or equal to 1, so from a linear equation on up, has at least one complex 0. So if I have a polynomial that is complex parts, it has at least one complex 0. Okay. A follow-up to that, every complex polynomial of degree n greater than 1 can be factored into n, not necessarily distinct, linear factors. Which means it has n complex zeros. Now, complex zeros also include real zeros in there. What the fundamental theorem of algebra is saying is that every single polynomial with real coefficients has zeros, real and or complex, and you can find those zeros. They exist. It is factorable. Every single polynomial is factorable. That's what the fundamental theorem of algebra is saying. It says that you can solve it. Now, your solutions may be in the complex realm, but it has solutions. There are problems. There are many, many math problems that are not solvable. There are many, many math problems that have no solution. Polynomials are not one of them. That's a very powerful statement to say that if you have a particular type of an equation, you can find a solution no matter what. Now, your solutions may be complex. They may not be real solutions, but you can find solutions to any polynomial no matter what. They are there. That's a very, very powerful statement saying that you can solve a particular type of problem every single time no matter what. That's a huge, huge statement. Okay. So the conjugate pairs theorem. Given a polynomial with real coefficients, if a complex number z, and z is what we refer to as complex numbers, that z is a 0, then its conjugate is also a 0. In other words, if a plus bi works, a minus bi works. In other words, every single complex solution to a polynomial comes in pairs. You will never have a single complex solution to a polynomial. All complex solutions Any solution that has an I as part of your answer will be part of a pair. They never, ever, ever come alone. They always come in pairs, which is also a very nice thing. So if you find one, you know automatically you have another one just like it, only the signs are changed. Okay? So it's a very powerful thing. I have zeros. I can find the zeros of any polynomial. And if one of my zeros is a complex number, then that complex's number conjugate is also a zero. Okay? They come in pairs. So if you have a polynomial of an odd degree, if the complex ones only come in pairs, that means you're guaranteed to have at least one real coefficient. And if you think about the graph, what does it do? The graph crosses the x-axis somewhere, at least once. To go from negative to positive, you got to be zero in between. And if it crosses at least once, that means you have at least one real solution. The rest of them may be complex, but they all come in pairs. So if I have a cubic, I'm either going to have one real solution or three real solutions, because I'm not going to have two real and one complex, because complex solutions always come in pairs. I will either have no complex solutions, or 2, or 4, or 6, or 8. I will never have an odd number of complex solutions. Okay? Those are some powerful tools for solving polynomials. Okay? So let's do this. Let's find all the complex zeros of those two equations. Now the first one, okay, we don't look for the complex zeros just to look for complex zeros. We don't do that just because. We want to find the real ones first, because the real ones are easier. We only go with the complex because, frankly, we have to. Okay? So I look at the first one, x squared minus 4x plus 13. The first way I want to try to solve this problem, if I can, is by factoring. If I can factor, I want to do that. Can I factor that quadratic? No, there are no numbers that will apply to give me 13 that will ever combine in any way, shape, or form to give me negative 4. And it can happen. So I have to use the quadratic formula. Or, as I mentioned in the last class, you could, if you really want to, use completing the square. I hate completing the square. I never use completing the square unless I have no choice in the matter. What? It depends. It depends on what you're comfortable with. Like I said, I don't like it. To me, it's more of a pain. It's either factoring a quadratic formula for me. Now, if you want to do completing the square, go right ahead, knock yourself out. I don't like it. Part of the reason is if I have something instead of just x squared in the front, completing the square is really a pain in the butt, because then you got fractions involved. And if it's an odd term in the middle, then you got fractions involved. With an even term, this one wouldn't be too bad. So x equals minus negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 13 all over 2 times 1. So I get 4 plus or minus the square root of negative 36 over 2. What's the square root of 36? 6. What's the square root of negative 1? I. So I have 4 plus or minus 6i over 2. Divide everything by 2. 1 plus or minus 3i. How many zeros do I have there? Sorry, 2. You're right. 2 plus or minus 3i. I have 2 zeros, 2 plus 3i, 2 minus 3i. Those are the conjugates that they told me I would have. The same except for plus or minus between the two numbers. And only between the two numbers. Okay. And then, so that's only actually half my answer. It says to find the zeros. The other part says to write them as my factors. So I have x minus 2 plus 3i, x minus 2 minus 3i. Those are my two factors. Those are my zeros. Those are my factors.
Yeah, it will always be x minus 2.
Yep. Now you can simplify it and distribute the negative, get rid of the parentheses inside the parentheses if you want to, but it doesn't bother me. Okay, this one's a little more fun. X to the fourth minus 16. And yes, it is factorable. I have the difference of two squares. X to the fourth minus 16 is the difference of two squares. What is the square root of x to the fourth? X squared. What's the square root of 16? 4. So this is x squared minus 4, x squared plus 4. Can I factor x squared minus 4? Yeah, that's the difference of two squares. X minus 2, x plus 2. So there's two of my factors right there, and my zeros from that are plus and minus 2. Is x squared plus 4 the difference of two squares? No, it is the sum of two squares. However, it really is not that difficult to solve. X squared plus 4 equals 0. Subtract 4. X squared equals negative 4. Square root both sides. X equals plus or minus the square root of negative 4. So x equals plus or minus 2i. 2i. Square root of negative 4 is 2i. Plus or minus 2i. So that means I have zeros of plus or minus 2, plus or minus 2i, and x plus 2i, x minus 2i. Said not too bad. I didn't say it was easy. Questions before moving forward? Okay. Ooh, it's a fun one. Okay. Find a polynomial of degree 4 with real coefficients such that 1 is a 0 of multiplicity 2 and negative 4i is a 0. Sorry, negative 4 plus I is a 0. Well, if negative 4 plus I is a 0, what else do I have for a 0? Negative 4 minus I. If you're given one complex 0, its conjugate is also a 0. So I have all of my zeros. Okay? So I have negative 4 plus I, negative 4 minus I, negative 4 minus I, and then I have 1 with a multiplicity of 2. So that means I have x minus 1 squared. That's where 1 with the multiplicity of 2 comes from. And then I have x minus negative 4 minus I, x plus, x minus, I keep doing this, x minus negative 4 plus I. Yes.
How did you get those?
Because what are my two zeros? These are my two zeros. It's x minus the first and x minus the second. Whenever you're given one complex, you know you have two. You have the one in its conjugate. Now, fun part. X minus 1 squared is x squared minus 2x plus 1. Okay, now I got to multiply this one here together. What do you mean, how did I get this? I took x minus 1 and I squared it.
So this might be like a question, but why is it x minus the 0?
Because it's always x minus whatever your 0 is. It's x minus c every time. X minus 0. Remember, your zeros are the opposite of what's inside the parentheses.
Right.
So if I factored it out and I got like x plus 2,
Yeah, so it's
minus 2 would be my 0.
the opposite of nothing, right?
Right. So on this one here, okay. On this one here, distribute the negative to get rid of the inside parentheses. X plus 4 plus I times x plus 4 minus I. And then there's no real easy way to multiply this one out. So what I did was I just multiplied everything times x, everything in the second one by, I just basically did distribution. So if I do that, I take the x's through, I get x squared plus 4x plus, or sorry, minus ix. Multiply everything through by x, multiply everything through by 4, plus 4x plus 16 minus 4i. And then I multiply everything through by I times x, ix, I times 4, 4i, and I times negative I is negative I squared. Notice how I wrote my problem. Look what happens to your i's. What is I squared? What is I squared? Negative 1. So what is negative I squared? Plus 1. So this becomes plus 1. So now I have x squared plus 8x plus 17. It's originally minus I squared on the end. Now if you FOIL that out and multiply that out, you get x to the 4th plus 6x cubed plus 2x squared minus 26x plus 17. Yes, part of the reason why, and you'll notice, so we had complex zeros because we get any complex numbers for our coefficients. No, when you have the conjugates, the complex part falls away when you multiply it. Okay. So it seems like although we have I as a solution, we do not have I in the original problem. And I know this is something that when I do this in Algebra 2, when we talk about I, students often, well, why do we have imaginary numbers? Why does it matter? Why do we want to use something that doesn't actually exist? I'm going to tell you right now, if you are solving problems involving electricity and magnetism and physics, and you do not get I as part of your solution to your problems, you did it wrong, and what you were working on will not work. It blows my mind. My father was an electrical engineer, and he and I had discussions about this more than once. When he was designing his electronics and the circuitry and everything else to see if they work, he had to do the problems to make sure everything he had was going to work. And if he did not get I as part of an answer to a real world design that he was working on, what he was working on would not work. It is absolutely mind-blowing to me that that was the truth. That you had to get an imaginary number as a solution to a real problem, or your real thing that you're working on would not actually work. It is bizarre. And I had physics problems like that in college that worked out. And it's still like, it can't be right. I can imagine it was right. Yeah. So it's really weird. Okay. Let's look at the next one. Find a real polynomial with degree 3, which means how many zeros do I have to have? 3 zeros. With real coefficients such that I and 3 are zeros. and f of 4 is 34. So I have two conditions I need to meet here. I need to find a polynomial of degree 3 with zeros I and 3. Yeah, and if I have I, what else do I have? I have negative I to go with it. So if I have this, that means I have negative I as well. So my three zeros are x minus 3, x plus I, x minus I. Now, when you FOIL this out, x plus I times x minus I, exactly the same except for plus and minus, right? So what do you get? You get x squared minus I squared. I squared is negative 1, so x squared minus negative 1. I have x plus 3 times x squared plus 1. FOIL those out, and you get x cubed minus, sorry, this is supposed to be a minus 3. My bad, minus 3, that's my bad. X cubed minus 3x squared plus x minus 3. So that is my first condition that I have met. Polynomial degree 3 with real coefficients such that those are my zeros. So I start with my zeros, FOIL it out, there's my polynomial. I do not know if I have yet met my second condition. What I need to do is I need to figure out, is this true? So I plug 4 into here. 4 cubed minus 3 times 4 squared plus 4 minus 3. I do that, what do I get? I get 17.
So it doesn't work.
However, what can I do to 17 to get 34? Multiply by 2. And if I take this times 2 and that times 2, do I get the same thing?
Yes.
So what do I need to do? I need to multiply this times 2. Because if I get 17 when I plug in here, how do I get 34? I take it times 2. Distribute by 2. 2x cubed minus 6x squared plus 2x minus 6. And if I plug 4 into that, I'll get 34. Okay. Will that give me the same zeros? Yeah, if I set that last one equal to 0, what's my first step I'm going to do? Factor out a 2. Divide everything by 2, because everything's divisible by 2. Make it a simpler function. Divide everything by 2. That's my first step in trying to solve it. And if I do that, then what do I get? I get the one above, and then I factor it, and I get the factor that I started with. So yeah, that will work. Questions? Yes.
I don't really know how to word this, but it's a very nice situation where you're trying to disprove the conditions, like if you're doing wrong, you have to say like inside.
It's extremely easy to prove that something is not a 0. Plug it in and it'll get 0. So that's a very easy thing to do. So that's really probably not something we're going to do a whole lot of. And that would also be covered by the beginning of what we did. Okay. So this is similar to what we left off with on Thursday. Find all the complex zeros, it should say zeros in the given function, write it in factor form. So the 0 is missing from your thing. So what would we start with? All the factors of 68 divided by all the factors of 1, which is all the factors of 68, plus or minus 1, plus or minus 2, plus or minus, oh my god, I don't want to do all of those. Okay. So where would I start? I would start with 1, plug in 1, do I get 0? No. Plug in 1, do I get -1, do I get 0? No. So then I would go to the next easiest one. I'm not going to start with 68. I don't want to do long division. I don't want to work with 68. It's a pain in the butt. So I would try 2. Now, on the original notes that I had, it said to use your calculator to get a starting spot. I'm telling you, use 2. You won't be able to use a calculator on your test. That would help you with this anyways. So I'm telling you, we're going to go to 2. So we're going to check 2 for a root. Okay, how do I do that? Synthetic division. So I have 2. 2 is a 0, which means, and once it in factored form, I have x minus 2 as one of my factors. Now I want to do the same thing again with x cubed minus 4x squared minus plus 21x minus 34, because that's my polynomial I have left over. I'm not going to go back and work with the original one when I can work with something smaller and easier to work with.
How do you know when to stop? If you want to get through like that, say now we have to do it again. How do you know to stop?
Because I don't have all my factors, I need 4 of them. Because I started with 4. The 4th power, I have to have 4 zeros. I've only got 1. I got to find more. So I got to do the same thing again. I put in 1, that doesn't do it. I put in -1, that doesn't do it. Once again, I'm starting with smaller numbers. So I would do 2 again. And guess what? It works again. So that means I have x minus 2 squared. There are 2 of my zeros. It is okay to have 2 zeros. Yes.
Wouldn't the 4 21 be negative because you multiplied it?
You're right. I did the math right. I just didn't write the number right. My bad. Thank you. So now what do I have left? X minus 2x plus 17. It's quadratic. Do I need to go through all this rigmarole for a quadratic? No. So what are you going to do? See if you can factor it. If that doesn't work, and there are no 2 numbers multiplied to give me 17, combined to give me 2. So guess what? Find the complex zeros. Do that. I'm tired of doing all the work. So, quadratic formula, leaving the square, either one, you get 1 plus or minus 4i. Which means you have x minus 1 plus 4i, x minus 1 minus 4i. Yes?
The quiz is going to be multiple choice, right?
Not now.
That's me. That's my
I'm going to fail it then.
You gotta wait till we take the quiz, and you got 2 weeks till we take the test.
Wait.
What?
When is the quiz?
What does it say on your schedule?
Next week. It says next week.
Okay. Last problem. Use the given zero. What?
For the last problem, we just leave it in the
In factored form. So the last one, find all the, use the given zero to find the remaining zeros.
Plus 2i.
Yeah, so there's one of them. If I have minus 2i, I have plus 2i as a zero. Okay, so I have 2 of my zeros right there. Now I have to find the others. So here's what you want to do. You want to make that simpler. You don't want to go looking for your zeros in the original problem if you can make it a smaller one. That's not that difficult to do. First thing you do is, if these 2 are zeros, that means I have factors of x plus 2i, x minus 2i. And if I multiply those out, I get x squared plus 4. Now, one of the earlier ones we used, one of the earlier problems we used, or one of the earlier things we used in this class was, if I take a polynomial, divide it by a factor, the remainder, or I should say the answer I get, is also a factor. So if I take my original polynomial, divide it by x squared plus 4, I get my other factors, and I can factor that out at that quadratic. So I have to do long division. So I have x squared plus 0x plus 4. And yes, it is important to put the 0x in there. And that goes into 2x to the 4th plus 5x cubed plus 5x squared plus 20x minus 12. And I'm going to move this. Okay. Now, as a reminder with long division, all I care about is how many times does this first term go into this first term. Everything else just goes along for the ride. So how many times does x squared go into 2x to the 4th? 2x squared. Where do I put that 2x squared? Where on the top? Because that is important. That's over it. And on the top, it's over it now. It has to be over the x squareds that are there. It has to line up. It has to. This is the rules of long division that you did last year in Algebra 2. It has to line up. Excuse me. It is. So it has to line up. Multiply it out. 2 times x squared, 2x to the 4th. 2x squared times 0x squared, 0 times 0x is 0x cubed. 2x squared times 4, 8x squared. Subtract. 2x to the fourth minus 2x to the fourth, gone. 5x cubed minus 0x cubed is 5x cubed. 5x squared minus 8x squared, negative 3x squared. And then bring down the 20x. How many times does x squared go into 5x cubed? 5x times. So I put plus 5x. 5x times x squared. 5x cubed. Plus 0x squared. Plus 20x. Subtract. 5x cubes are gone. Negative 3 minus 0, that's negative 3x squared. 20x minus 20x plus 0x. Bring down to minus 12. How many times does x squared go into negative 3x squared? Negative 3 times. Negative 3 times x squared, negative 3x squared, negative 3 times 0x is 0x, negative 3 times 4 is negative 12, and you subtract, and you get nothing. It goes in evenly. So I have x squared plus 4 is one factor, 2x squared plus 5x minus 3 is my other factor. And now you factor this quadratic. And that's easy. And that's it.